Quenching and tempering of steel. The annealing processes presented in the linked video were mainly concerned with improving the manufacturing properties of a workpiece, such as formability or machinability. However, in many cases high hardness or strength is required. An example of this is a file that is used for machining workpieces. In order for the file to be able to remove the material from the workpiece to be machined without itself becoming blunt, it must be wear resistant and thus very hard. Gears and gearboxes also have to be very hard and wear resistant on the flanks. This is the only way to ensure long life for the gears and the gearbox. A gear shaft is an example of a case where high strength with good toughness is required, but not necessarily very high hardness. It is subjected to high loads from the engine and must therefore have a high strength. At the same time, however, it must have a certain toughness in order not to break immediately under elastic deformation. Depending on whether high hardness or high strength with good toughness is required, the special heat treatment processes of hardening and tempering have been developed. Both hardening and tempering are basically carried out in 3 steps. In the first step, the steel is heated to relatively high temperatures. In the second step, the steel is quenched, which means it is cooled very quickly. In the third and final step, the steel is reheated and then slowly cooled, a process known as tempering. Depending on whether the aim is to achieve high hardness or high strength with good toughness, tempering is carried out at different temperatures. If a steel is to be very hard, it is only tempered at relatively low temperatures in the range of 200 degrees Celsius to 400 degrees Celsius, while at higher temperatures in the range of 550 degrees Celsius to 700 degrees Celsius it becomes tougher and highly stress resistant. In the following, the microstructural processes during quenching and tempering are discussed in more detail. At this point, a brief note on the heat treatment processes such as normalizing, soft annealing, coarse grain annealing, recrystallization annealing, diffusion annealing, or stress relief annealing. Whereas in these so-called annealing processes the driving force for the respective microstructural change is always the achievement of a lower energy state, that is, the establishment of a thermodynamic equilibrium, quenching and tempering involves a thermodynamic state of disequilibrium of the microstructure. The establishment of thermodynamic equilibrium is specifically prevented by rapid cooling. Because of these fundamental differences, quenching and tempering are usually listed separately from the aforementioned annealing processes. The microstructural changes of the steel during the individual steps of quenching and tempering are discussed in more detail in the following. As mentioned before, the first step is to heat the steel above the GSK line in the iron-carbon phase diagram. This completely transforms the body-centered cubic ferrite lattice into the face-centered cubic austenite structure. This is why the process is called austenitizing. During austenitization, the cementite in the perlite decomposes and the carbon released becomes soluble in the austenite lattice. In order for the perlite to decompose not only in the peripheral zone of the steel but also in the interior, the workpiece must be held at temperature for a long time, depending on its thickness. As already explained in more detail in the linked video on the iron-carbon phase diagram, the carbon atoms in the austenite lattice each occupy the space within the face-centered cubic unit cells. If the steel were to cool slowly again in this state, the austenite lattice would change back into the ferrite structure, which is almost insoluble for carbon. Due to the relatively slow cooling, however, the carbon atoms would again have enough time to diffuse out of the transforming austenite lattice and form cementite. Slow cooling from the austenitic state would only restore the original microstructure. The desired microstructural change would not occur. Instead, it must be cooled relatively quickly. This is the next step in the process, which will be explained in the following. If the steel is cooled from the austenitized state not slowly but relatively quickly, the dissolved carbon does not have sufficient time to diffuse out of the austenite lattice. Such rapid cooling is also referred to as quenching. Quenching can be achieved, for example, by immersing the workpiece in water or oil. During quenching, the carbon remains forcibly dissolved in the forming ferrite lattice despite the lattice transformation. The body-centered cubic unit cells of the ferrite are tetragonally expanded by the carbon atoms forcibly dissolved in them. In principle, steel contains fewer carbon atoms than there are unit cells. Therefore, not every unit cell is tetragonally expanded. As a result, the lattice is highly distorted. This distorted microstructure is very hard, in contrast to the original ferritic microstructure. In addition, the lattice distortion leads to an extremely strong inhibition of dislocation movement. As a result, the formability of the steel is greatly reduced, while the strength is increased. The tetragonally expanded lattice structure ultimately represents a new microstructure, which is called martensite. Under the microscope, martensite is recognizable as a needle-like or plate-like microstructure. So note, pure martensite is very hard and is largely responsible for the increase in hardness and strength after quenching. Note that the formation of martensite can no longer be explained by the iron-carbon phase diagram, since such diagrams are basically only valid for relatively slow cooling rates, at which a thermodynamic equilibrium can always be established in the microstructure. However, thermodynamic equilibrium is deliberately prevented during quenching. The iron-carbon phase diagram is therefore no longer valid in this state. A disadvantage of the high hardness and strength of the martensite microstructure is its enormous brittleness. Pure martensite has no slip planes and therefore cannot be plastically deformed. Especially in hypereutectoid steels, considerable embrittlement occurs due to the additional cementite at the grain boundaries. For this reason, hypereutectoid steels are often soft annealed beforehand. However, after quenching, the steel is virtually unusable. It can hardly be deformed under load and breaks immediately. Even a bump on a hard floor will cause the quenched steel to break. This is why the state of steel after quenching is called glass hard. To make the quenched steel ductile again, the microstructure has to be heat treated again. This is done by reheating the steel. However, the temperature remains below the GSK line, which means that the microstructure is not converted back to austenite. This reheating to relatively moderate temperatures is called tempering. Due to the increased temperatures during tempering, the carbon atoms that are forcibly dissolved in the martensite can partially diffuse out again. As a result, the tetragonal martensite recedes and the lattice distortion is partially reduced. Hardness and strength are somewhat reduced, but the steel gains considerable toughness. After tempering, the steel is usually cooled slowly in air. Note that the martensite microstructure after quenching is ultimately a state of disequilibrium, as the microstructure could not reach thermodynamic equilibrium due to the rapid cooling. However, the subsequent heating during tempering gives the microstructure time to develop towards thermodynamic equilibrium again. This results in the diffusion of carbon from the martensite lattice. Although hardness and strength may have decreased after tempering, they are still well above the original microstructure before quenching. Depending on the temperature and duration of tempering, properties such as hardness, strength, and toughness can be specifically controlled. The temperatures required to achieve certain properties can be found in so-called tempering diagrams. The diagram shows the tempering diagram for a carbon steel containing 0.45% carbon. In general, the higher the tempering temperature and the longer the tempering time, the greater the increase in toughness, while the hardness and strength values decrease. Thus, there are basically two different ways of controlling the process, depending on the material property to be achieved. If the steel is to be very hard and wear resistant, a high degree of hardness is required. The steel is therefore tempered at relatively low temperatures. This process is known as hardening. The steel is then called hardened steel. If, on the other hand, the objective is to achieve high strength combined with high toughness, the tempering temperatures are chosen to be higher. This process is just called tempering and the steel is called tempered steel. But remember that hardened steels are also tempered, it's just a question of temperature. The shown stress-strain diagram shows a steel with 0.45% carbon once in the normalized, once in the quenched and tempered, and once in the hardened state. Note that although the hardened state is formally characterized by the highest strength, this high strength has hardly any practical significance because the hardened steel allows almost no plastic deformation. Even small deformations lead to an extremely strong increase in stress. In the present case, the stress already exceeds the maximum strength at a deformation of 2% and the hardened steel breaks. So note, hardened steels can only be used if deformation can be practically ruled out and ultimately only a high hardness of the steel is important. Quenched and tempered steel is significantly tougher than the hardened condition and can therefore be deformed to a much greater extent. Strength is also significantly increased compared to the normalized state. The yield point and tensile strength have almost doubled as a result of quenching and tempering, while the elongation at fracture is still relatively high at 14%, so the quenched and tempered steel retains high toughness. So note, a quenched and tempered steel is characterized by high toughness combined with increased strength. Because of this combination of high strength and high toughness, quenched and tempered steels can absorb a large amount of deformation energy before fracture. This is shown by the area under the curve in the stress-strain diagram. The area under the curve is a measure of the energy absorption capacity of the steel. While the hardened steel can absorb very little energy, the quenched and tempered steel has a much higher energy absorption capacity. In addition to carbon, steel usually contains other alloying elements such as chromium, nickel, vanadium, or manganese. How these affect the formation of martensite is explained in the following. Basically, the following requirements for the quenching and tempering of a steel result from the process steps mentioned, which will be discussed in more detail in the following. First, carbon must be soluble in gamma iron and insoluble in alpha iron. Second, the gamma-alpha transformation must be present and not suppressed by alloying elements. Thirdly, there must be sufficient carbon to give a significant increase in hardness or strength and to make hardening and tempering economical. In some steels, such as the stainless chromium-nickel steels, the gamma-alpha lattice transformation is prevented by the addition of alloying elements such as chromium and nickel. Depending on the alloying elements, the steel either remains in the austenitic state up to room temperature where the austenite phase is completely suppressed and the steel remains in the ferritic state over the entire temperature range. Such ferritic or austenitic steels cannot be hardened because the necessary gamma-alpha lattice transformation is missing and therefore no martensite can form. Another prerequisite for the hardenability of a steel is a sufficiently high carbon content. Too little carbon would result in no significant martensite formation. Although there would still be a small increase in hardness or strength, this would not justify the relatively high cost of the process. As a guideline, hardening is only economically and technically feasible from a carbon content of about 0.3%. The key to martensite formation is to prevent carbon diffusion during the gamma-alpha lattice transformation. This is achieved by a sufficiently high cooling rate. If the cooling rate is too low, not enough martensite is formed. The carbon atoms can still partially diffuse and form cementite. An intermediate microstructure is formed which, in terms of its properties, lies between the perlite microstructure and the martensite microstructure. This intermediate microstructure is also known as bainite. In general, a completely martensitic microstructure should be aimed for when hardening. In principle, the cooling effect during quenching is greater at the surface of the workpiece than in the interior. As a result, the critical cooling rate required inside the workpiece to form martensite may not be achieved. Only the surface of the workpiece is hardened. This is particularly the case with unalloyed steels with a relatively large cross-section. Such steels, which cannot be hardened over the entire cross-section, are also known as surface hardening steels. Even higher cooling rates to achieve complete hardening have their limits. Extreme cooling rates can lead to high thermal stresses in the component, resulting in so-called quench distortion or even cracking. To achieve hardening over the entire cross-section of the workpiece, carbon diffusion has to be inhibited. After all, the formation of martensite is caused by the obstruction of carbon diffusion during lattice transformation. This can be achieved by the addition of alloying elements. In principle, it is irrelevant which alloying elements are used, since each alloying element obstructs carbon diffusion to a greater or lesser extent. Ultimately, all the alloying elements act as additional barriers to the diffusion of carbon atoms. As a result, high-alloy steels generally harden through the entire cross-section compared to unalloyed steels. High-alloy steels therefore require a lower critical cooling rate during quenching in order to form martensite. In principle, the cooling rate should only be as high as necessary for martensite formation. At the same time, it should be as low as possible to minimize the risk of quench distortion or cracking. The cooling rate can be influenced by the choice of quenching medium. While unalloyed steels generally have to be quenched in water, a milder quenching medium such as oil is sufficient for low alloy steels. In the case of high alloy steels, however, quenching in air can already lead to martensite formation. Accordingly, these steels are also referred to as water hardening steels, oil hardening steels, or air hardening steels. A cold work steel to be hardened will serve as an example in the following. The austenitization temperature of this steel is about 1020 degrees Celsius. It is heated for approximate 25 minutes. Then this high alloy steel is quenched in air. After quenching, tempering takes place at around 300 degrees Celsius. As a second example, an unalloyed steel with 0.45% carbon is considered for quenching and tempering. In this case, the austenitization temperature is around 840 degrees Celsius. This unalloyed steel is then quenched in either water or oil. After quenching, the steel is tempered at 550 degrees Celsius if quenched in water, or at around 660 degrees Celsius if quenched in oil. The comparison of the two steels again clearly shows that unalloyed or low-alloyed steels have to be cooled in stronger quenching media than high-alloyed steels. On the other hand, it is again evident that the tempering temperatures are lower during hardening. I hope you enjoyed the video and found it helpful. Thanks for watching.